Our Space Commander game models the game world as a two-dimensional map with all of the game objects moving inside it, obeying normal physics of motion. So we need to code this model and then translate the game world to our screen world so that the player can play the game. Let's see how that's done. Hi and welcome to Bytes and Bits. We've been coding our Space Commander game for a couple of videos now. We've got the vector graphics working and we're able to define, draw, rotate and scale the game objects. But we haven't yet looked at movement and how we're going to model the physics of our game's world. And that's what we'll be looking at in this video. Now, if you haven't seen the previous tutorials for this project, then please check out the description below for links, and don't forget to click on the subscribe button and notification bell to get hold of all my tutorials as I publish them. So let's get on with the coding. The Space Commander world is modelled as a 2D space, a bit like looking at a map from above. Objects in the game exist and move in this 2D space, and all our calculations will take place in this game world. When it's time to draw objects on the screen, we'll then map the game world to our screen world. To describe objects' positions and motions, we need to define a few parameters. So firstly, we can look at the position. So this is the X and Y coordinates of the object in our 2D game space. Now, screen coordinates tend to use the top left corner as the 0,0 origin position, with the positive x-axis to the right and the positive y-axis to the bottom. Now, this differs from the conventional mathematical axes, which have a positive x-axis to the right, but their positive y-axis is to the top. Now, it's really a personal choice, but I usually stick to the mathematical model unless the game world is very simple. But in this case, we'll be modelling vector quantities for velocity and acceleration, creating targeting code, etc. So using the mathematical model just makes it easier, at least for me, to see how the angles and positions all fit together. We can make the game world match the screen world, but it doesn't actually save that much computing power, and it makes it harder to get your head around the flipped mathematics. Now, we also need to model the direction. So when objects move or rotate, we need a way to describe their direction or the way they're pointing. Using normal mathematical notation, this gives us a 0-degree angle parallel to the positive x-axis, in other words horizontally to the right, with positive angles being measured anti-clockwise from this. So using this notation, it makes all our angles and the sines and cosines and tangent calculations all match up with what we would expect from our mathematics. So looking at distance, as our world is imaginary, we don't have to worry about real-world distance measurements. Our positions will be easier if we use pixel coordinates, so it makes sense to measure all of our distances in pixels as well. Considering time, again, we get to choose units of our time. We could use seconds, but a much more natural measurement inside our code is the game loop. So using one game loop as one unit of time, it simplifies the whole time process. If we set a speed of 5 pixels per loop, we simply need to add 5 pixels each time our game loop runs. But this method can have some problems. It does rely on the game loop running at a set speed. So in tick 80, our game loop runs at 60 loops per second. But if our code gets a bit too complex, each game loop can take a bit longer than this 60th of a second to complete. So our game will start to slow down, and objects will visibly move slower on the screen. Now, if you've ever played any retro computer games, you'll have seen this in action. We also want the player to be able to fly as far in any direction that they want, and this gives the idea of an infinite playing space. If we use standard position measured in pixels from a fixed origin, we'll hit a problem. So in computers, numbers have limits. if we use an integer variable to model the x-coordinate of the player, there'll be a maximum and a minimum value that this variable can store. So if you're familiar with other languages such as C, you'll understand about using different number sizes, different numbers of bytes to store our integers. So a single 8-bit byte, a single byte integer, that can store values from 0 to 255. A 16-bit integer can store values from 0 to 65,535, and so on. Now, if our player were to fly in one direction for a long time, the coordinates may reach the limits of our variable. For example, if we did use an 8-bit integer to store our x-coordinate, we can count up to 255, but as soon as we go 1 pixel further, this will result in an overflow, and our variable will wrap back round to 0. So to get around this potential problem, we'll use the fact that we always want the player to be in the centre of our play area. So we'll use the player ship as our origin and have everything else moving relative to this. So if the player ship is travelling up, we keep the player ship stationary but move everything else in the world down. And this then gives us the same end movement. Now in TIC80, which actually uses Lua, all of our numbers are represented by 64-bit floating point numbers. And this means that in reality, we're never going to get a problem with our variables overrunning, because the maximum intervalue that we can get up to is either positive or negative 2 to the power of 53. And that is a very, very big number. So you'd have to be traveling for days in one direction. But do be aware, do be aware that this is a problem if you're coding in languages such as C, and you do need to pay attention to the size of your variables. And at least now you will know what will happen if you do that. So we also need to model the position and movement of our objects. We know the basics now and the basic parameters that we're going to use to model our data. But we want to create several helper functions that will allow us to calculate positions, movements, rotations, and so on. Now we're going to have a few different types of objects, such as our player ship, enemy ship, missiles, stars, etc. And we could write separate functions for each of these objects, for example, to rotate them. But each of these functions would be basically the same code repeated multiple times, and this isn't good coding practice. So we want each operation to be handled by a single helper function, which will be able to work with all our objects. For example, we want to create a rotate object function into which we can then pass either a player ship or an enemy ship or whatever. And this should then work out those calculations based on whatever we supply it to. Now this relies on each object in our game storing its model data in a same format. So when we create a class or an object definition of each game object, it will inherit this data format. And this is one of the principles of object-oriented programming, or this idea of OOP, and we call this inheritance. Or we can think of it as each object providing a defined setup to its values. And this is an object-oriented programming interface. Now, if you're interested in learning more about object-oriented programming, please check out some of my Python courses on Udemy, where I cover this in much more detail and take you through the full coding and theory of object-oriented programming. Now in TIC80, we'll have to implement this idea of inheritance or interfaces manually. But as I say, in other languages such as Python, they have that built into their object-oriented programming system. So each object in our game is going to have a position attribute with an x and y coordinate and a velocity attribute with an angle and a magnitude. So if we want to move our objects in this 2D world, as we've already seen, the player ship isn't going to move, and its position will always be at the origin 0, 0 in pixel coordinates. But it will have a velocity and an angle and a magnitude. So to move the player ship, we need to work out its x and y position increments. So in each tick it will move at a small increment, and we can term these dx and dy. And we have a formula for working these out, where we're simply multiplying the velocity magnitude by either the sine or the cosine of the velocity's angle. When we come to model the movement of each of our other objects, so again, because we're modelling everything with vectors with a magnitude and direction, we can simply calculate the incremental movements due to their motion and simply add that on to their current position, and that will give us then the overall movement of each object in each of our time periods. So all the previous calculations allow us to move our objects around in our 2D game world, where we are obeying all the mathematical norms for the axes and angles. We now need to work out how to draw this on the screen. So we know that we always want the player ship pointing vertically, and this is a 90-degree angle measured from our positive x-axis. So if the player ship is currently travelling at an angle A, or omega, we would need to rotate the game by 90 minus A degrees to get the ship pointing up the screen. Our screen coordinates are measured from the top left corner, with x increasing to the right and y increasing down the screen. So to map our 2D game world to the screen, we need to take the game world x coordinate, but the negative of the y coordinate. We then need to offset this by half the screen width and half the screen height to move the origin into the centre of the screen. And this will leave our new position with the actual screen coordinate version of our game world position. Also, as we rotate an object around the origin to position it on the screen, its coordinates will change, but so will its angle of rotation. We know that we need to rotate the game world by 90 minus the player's ship angle, so when we draw an object on the screen world, its rotation will also increase by this same amount. So we've now got all the information and calculations we need to code this game world and map it onto our screen. So let's have a look at the actual code. So moving into TIC 80, I've got a little demo program here which lets us have a play with these helper functions. Now if you have a look in the description below, you'll see there are links to my main project page on my bytesandbits.co.uk website, and there you'll be able to download the files for this and view the code. So you can have a bit of a play with it yourself. But what this program lets us do then is we have the player ship fixed in the centre of the screen, but we now have the ability to move that ship. So if I use my left and right arrow keys, you can see that then it's rotating the player ship, but of course we have coded it so that the player ship remains stationary and the world rotates around it. And we can then of course start moving forwards and backwards and so on. I've also then coded there to be 4 enemy ships in the area, and you can see those showing there. So I've upgraded our enemy ship drawing routine to have all 4 enemy ship types in there. And we can see that as we rotate those, they do behave correctly as we move around the world. So in effect they are stationary within this world, and my player ship is the one which is moving through it. But of course we're getting that sort of effect happening with the player ship staying stationary. So let's go inside the code and see how that's done. So we have a block of code at the top which is part of the main sort of getting everything up and running. And again, we'll talk through that when we come to do the final setup for the game. But really what's happening is we need to set up the player ship and the enemy ships. And you can see in this little function here where we're initializing our variables, we are creating our player ship and initializing that. So we create an object, an empty object here called player ship, and then we start adding in these attributes to it. And the two we've been talking about are the position object. So we're saying we have here the player ship position, and that then is an object itself with an X attribute and a Y attribute. And again, these are the X and Y coordinates of the ship in the game world. And then similarly we have then the player ship velocity, which has both a magnitude and then an angle. And I'm initializing the angle to be 90 degrees so that our ship actually is pointing directly upwards, so that when we come to translate this onto the screen, we're not actually going to have to make any movements, because remember, we rotate the world by 90 degrees minus this angle to work out the relative change going from the game world to the screen world. So this just simply means that when we start drawing it, our player ships are actually pointing on screen in the direction that we're going to be setting them. So that's the player ship, and I say these are the two objects then within the player ship which our helper functions are going to assume are there, and that they describe both the position and the direction and the velocity of our object. You can see then we have got a little movement object here, and that's going to store the current change in position for both the x coordinate and the y coordinate of our player ship. So remember, whenever we start moving the player ship, we're going to need those values to adjust the positions of all the other objects in our game. Okay, so some of the rest of that then, of course, is for the main gameplay when we finally get to that. Well then, if we come down a bit further, we have our main tick function, and underneath that then we have our spawn enemy function. And again, at the moment this is just doing a test one, which is simply going to spawn in those 4 enemy ships. But again, you can see here we are creating our enemy ship object, which is in this line here. We are then giving it a position attribute, which is an object in itself with an x and y coordinates, and our velocity again with a magnitude and angle. And again, that actually copies the layout then for our player ship. So any object which has a position attribute with an x and y coordinates and a velocity attribute with a magnitude and angle, if we pass those into our helper functions, our helper function will be able to pull that data from it and understand how that particular object has been arranged. So let's come down a bit further here, and you can see we have lots of other information then that goes into the ship describing its movement. But let's go down and find some of our helper functions. If we look at our tick function first, so remember this is the main loop of our game, which runs 60 times per second. So really we're checking to see if this is the first time our game has gone through the loop, and of course that's where we actually then spawn our enemy ships and so on. But our main code then comes in this block of code here. So we're running through a number of functions which will update the various parts of our game. So we're going to update our movement parameters, and that's where we'll work out how far the player ship has moved. We're then going to move our background stars. We're then going to check our player ship's movements. We're then going to move our enemy ships and then draw everything on the screen. So let's work our way through the code for this. So if we go to our update movement parameters, so let's come down here and find that piece of code. So there's our update movement parameters. So this is where we are doing that calculation to work out how far the player ship would have moved in this particular time period. Remember, one time period being 1 click. So we have here our player ship movement. Remember, that was one of the objects we put inside our player ship, and we have this dx value, which is the incremental x coordinate value, and that then is the player ship's velocity magnitude times the cosine of the velocity angle. And again, that's what we looked at when we were going through the theory for this. And again, our incremental y position is the similar idea, but this time using the sine of our angle. So that tells us, because we're using pixels as our distance measurement and we're using 1 tick as our time measurement, that then gives us the number of pixels per tick that the player ship is currently moving in both of those directions. And we've seen then that that's what we'll be using to update the position of all the other objects in the game. So if we go back up to our tick function, We will see then that we are updating our background object, which I'm going to leave for now. We're then doing a check for our ship rotation and our ship acceleration, and that's just really looking at the keys that we move our ship with to make sure that we are controlling that correctly. So our player ship rotation, so if we're using the button 2, then we're going to increase the angle of our player ship. Remember the angle in which it's pointing is the actual angle in its velocity. So we're going to increment that by a small amount. If we press button 3, which is the right arrow, then we're going to take a little bit of angle away from that. And then we are using a little function here. So as our angles are incremented and decremented, they can get quite large. So remember, we're using radians for our angles, so they should be between 0 and 2 pi. And of course, if we simply hold down, say, the left arrow button, we will simply rotate in an anti-clockwise direction, and our angle will get bigger and bigger and bigger. And again, it'll go past 2 pi and then go past 4 pi as we keep rotating. So we just have a little function here called wrap angle, and what that will do, it will have a look at the angle we supply it. And if that angle is outside of the range 0 to 2 pi, so either greater than 2 pi or maybe it's gone negative, it will pull it back into the correct angle within our normal range. And again, from a coding point of view inside the computer's not so worried about that. But if we ever try to have a look at what's happening inside our code and do some debugging, then obviously if we have an angle which is sort of 50,000 degrees or whatever, it becomes harder to work out exactly what's happening inside our code. So this just simply makes sure that it's more human readable rather than anything to do with the processing inside the machine. Of course, if you are using other languages and you're using very smaller precision variables, so like an 8-bit variable to store this information, then obviously as you get bigger and bigger values, you do have that problem of the overrun. So do bear in mind. I say it's in this particular game, I'm doing it just so I can see what the angles are and just so it keeps them in a sensible range. But I say, in our particular instance, it's not such an issue. After we've checked the ship's rotation, then we need to check its acceleration. So that's really just looking at the forwards and backwards motion. And you can see here we're just checking our up and our down buttons. And the only way we need to work with there is the up button increases the velocity of our ship. So you can see here that we are then adding a little acceleration value onto that. And again, because we are keeping all of our units in pixels and ticks, so instead of this being meters per second squared and meters per second for our velocities, these are all in pixels per tick and pixels per tick squared and so on. And again, we can just choose those values just by trial and error. We're then limiting those values to maximum speeds and minimum speeds, and after that we are then just doing a bit of a check to see if we're very close to 0, then it will actually make it equal to 0, and that's just to make sure that we can actually come to a standstill. So that just sets up then our ship movement. So once our ship is moving, and of course at that point we will need to work out how far and how to move all the other objects in our game world. So if we go back up to our tick function, which is up here, we'll see that after we've updated our ship movement ideas here, we will then go off and need to move our enemy ships. So if I come back down and we'll find that piece of code. So that is down here. Okay. So at the moment, all we're doing in this particular demo is our enemy ships have not got any movement of themselves, so they are stationary within our world, which means that the only movement that we're going to have to consider is their movement relative to the player ship. So you can see here we have a for next loop which is going to iterate through each of the elements in this enemies array, and that array will hold each element will be one of the player ships. So we're then saying that our ship's position is going to be updated using this helper function called move relative to player. And that expects to have a position object being sent to it. So again, this move relative to player function, we're going to use that for every type of object in our game. So our enemy ships here, but when we come to do missiles and bombs and the stars in the background themselves, all of those will have to be able to be moved relative to the player ship, so that when our player ship moves, in effect we keep it stationary but then move everything around it. So if we have a look at that particular piece of code, we have here the function itself. So move relative to player. It expects a position or a point to be coming into it, and it simply moves that point relative to the player ship. So you can see here that it expects that point value, so the object being passed in, it expects it to have the x and y coordinates, and it simply updates those by taking away the player ship movement incremental value. So remember, we worked that out at the start of our tick function. So the player ship's movement for this particular tick, we've broken that down into an incremental x value and an incremental y value. So instead of the player ship being moved positively by those values, we're keeping the player ship stationary, and then everything else in the world is being moved in the opposite direction in effect. So that's why we've got this minus sign in here. So this will return back this object, which of course will have the x and y attributes in it, and that will then become the new position for that particular object. So again, that is moving each of the objects relative to the player ship itself, but this is all in the game world model. Okay. So in this test program, that's now moved everything inside the game world. So our game world has all been updated. And what we now need to do is to draw that on the screen. So our player ship drawing function is really just simply putting that icon in the very center of the screen. So if I come down here and find our draw ones, so we're drawing and draw background and draw player ship. So we've seen here that the drawing the player ship just simply puts that icon in the very center of the screen. The one which we need to look at though is how we draw the enemy ships. And we've seen then that everything in our game world doesn't directly translate to screen position. So we do have to modify and translate each of the position and velocity and direction values to make it look right on the screen. So again, all we're doing here is we are looping through each of the elements in our enemies array. So remember that each element is one ship. We're then updating its position to correspond to its screen display position, and then we're looking at the velocity, and we're translating that into a velocity as used on the display. Again, each of these two helper functions expects to have either a position being sent into it, so it can then translate that game world position to a screen world position, and then a velocity in this one here, and it will translate that velocity and angle into a screen velocity and angle. So if we have a look at those two functions then, so our translate position ones, so our position then, we can see that it is accepting in a parameter which we know is going to be a positioned object with x and y attributes. So we're saying here we're going to then obviously create a new position based upon that. So we need to adjust it by an angle, and we said here, so the angle which we need to adjust it by is 90 degrees, so in radians that is pi over 2, minus the player ship velocity angle, which is, of course, that's the direction in which the player ship is pointing. So our adjusted angle then whatever value we get, we're going to wrap that. So remember we used this wrap function a bit earlier on, and that's just simply taking our angle and putting it into the 0 to 2 pi value. So if we do get a value which is maybe negative or something like that, it will give it then as a positive angle, which is exactly the same angle as the negative value, but just in positive radians rather than any negative radians. We're then going to calculate, using that angle, we're going to calculate the new position. So we need to rotate our point around the origin. So remember, the player ship is actually at the origin of our game world. So we need to rotate this particular point around that origin by this angle, and that's what this rotate point function does for us. Now, if you've been following through the previous tutorials on this game, you'll know that we've actually used this function already. So this rotate point function, we use that when we actually draw our vector shapes. So again, this is just making sure that we create a series of general purpose helper functions that we can use throughout our game to perform the same operation over and over again. So again, we're simply rotating a point, we specify the origin around which we want to rotate it by, and then we give it an angle by which we want to do it. And that will return us back a position of this rotated point. And that's what we just simply then say here. So that's the rotated point position. And then, as we said in our discussions, to get that to be a screen display pixel value, we need to both invert the y value. So there we have our x value is staying as itself, our y value is being inverted, and then we're moving the origin into the center of the screen by giving it these little screen offsets. So at the end of this function, this new position object will be our input position parameter, which has been rotated, flipped, and offset so that it now is a true pixel coordinate for this point on the screen. So now we've got the position sorted out, we of course need to translate the angle of our object. And that was the second call that we made there, where we have this translate velocity to display. We're passing in the velocity attribute from our object. So remember, that's going to contain both a magnitude and an angle. In this particular function, all we need to do now is work out what is the angle that our object should be pointing when we draw it on our screen world. So we can see here we're creating a new velocity, and we're then assigning it an attribute. So the angle of that is going to be our existing velocity angle. So this is, remember, this is the game world angle, which is being sent in through this parameter. We're then going to add on 90 minus the player ship velocity. And again, that was from our discussions on how that works. So we then have our new velocity angle. We're wrapping it again so that it stays inside our 0 to 2 pi range. The magnitude, we're not having to adjust that because that of course just stays the same. All we need to do here is make sure that our ship is pointing in the correct orientation so that it looks like it is being moved around the player ship. And then we simply send that back, and of course that then is being stored within our drawing function. So if we go back down to our drawing function then. So now that we've got our screen position and in effect our screen angle worked out, we need to store that for this particular ship. So remember, we're working through each of our enemy ships. So we store the screen position inside our object. We're then doing a bit of a check here. So we can have a lot of ships flying around in our game world, but we won't be able to see all of them all the time. So there's no point in us going as far as drawing all the vectors which make up a particular ship if we can't actually see it on the screen. So all we're doing here is we're just checking if the current ship's position is outside of our visible range. So that's what we're doing here. And we're simply checking that as a rectangular area. We're not actually doing any sort of Pythagoras theorem or calculating distances. We're just doing a very simple, if it's too far off to the left or right or up or down, then we just don't draw it. But if it is within our visible range, then we are blanking out an object on the screen. So we're just drawing a little circle, and that gets rid of any of the background stars and so on. And then we're using our draw object function, which is the one we've been using all along. We are telling it to draw a particular type of ship. We're then giving it the position. So remember, this is now the screen coordinate position, and this is now the screen angle that we need it to be pointing in. And at that point, our drawing and movement is all finished. So if we go back to have a look at the running example then, so if we go back and do that, we can see here that when we start off then, remember we said that our ship was traveling at 90 degrees, so in other words, it's traveling directly upwards anyway, which means that when we draw our alien ships, which are spawned at an angle 0, then we can actually see them actually at that angle 0. So if I then rotate, we should find then that the ships both rotate around the player ship, but also rotate on their axes, so that they should always be pointing at perpendicularly to where the ship is. So if we come around here, you can see that we have that happening. So they are rotating around, and when we get back up to the top again, it's as if they had never moved. Okay, so that shows us then that our functions are all working correctly. If our ship starts to move, we can see that our player ship stays in the center of the screen, but it does look as if our player ship is actually moving. All the stars are moving correctly, all the enemy ships are moving correctly. So it does look like our player ship is moving through our game world, even though, as we already know now, our game world is moving around our player ship. So that is all of that bits of code working now. We can of course get a little bit more complicated with this. So if I load up a separate demo program here, so if I have a look and see what we've got in here, so it was the world rotate 2, and if I run that, we can actually code our player ships to move themselves. So what's happening here is, again, after we update our player ship movement, we then have a little piece of code which is going to continually just move our player ships, or sorry, our enemy ships, and constantly change their direction so that they simply move in small circles. And of course, our move enemy ships function now not only has to move them relative to our player ship, but they also then have to incorporate their own individual movements. And again, I'll put this code on the main project page so you can download that and then have a look at it. But it is pretty much just exactly as we've done, just with the added complication of putting in the enemy ship movements on top of that. So we've now got everything we need to model our game world, move all of our game objects inside this world with their positions and velocities and so on. We can then translate this game world onto our screen world so that we can display that then for our player to play the actual game. So the next things we need to do are to actually start building up the actual gameplay, and that's what we're going to work on in our next tutorial. So hopefully you've enjoyed this video. If you have, please do subscribe to my channel. Every subscription helps the channel grow and lets YouTube know that I'm actually producing some useful content. So I look forward to seeing you in one of the next videos, and bye for now. Don't forget to visit the course pages for this project. There you'll be able to download the code for this lesson and get lots of extra hints and tips. You'll also get access to all my other programming, electronics and gaming projects. All the links are in the description below. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.